Look here on the overhead screen, Colin, and see. So this is the mass spectrum here for an unknown compound X. And you can identify this highest peak up here as the molecular ion peak. That's generally where it will be, okay? The highest thing here, unless you have some impurity, whatever. Remember, there are sometimes these little isotope peaks, which are a little bit higher, and there is an M+1 peak you can kind of see right there. But what's the base peak? The base peak is the biggest one, and the tallest one with the highest number of ion counts hitting the detector is right here at 57. And that's an ion we've seen before. And then some others down here. And then there's the IR spectrum also here. And you can see a lot of frequencies down here in the fingerprint region. Remember down here below 1200 inverse centimeters, what's that? That's the bending region, the bond angle bending region. And those are coupled to a lot of other harmonic events or vibrations in a molecule. They can be very diagnostic. It is unique for an individual compound, but it's difficult to interpret to say what functional groups may be present only looking at this region down here. What's more diagnostic, more useful, is up here, the stretch region from 4,000 down to about 1,200. And a couple things really pop out there. The big carbonyl stretch right here, 1,700. Okay, and then the CH stretches right here. There's a couple little things up here you might be tempted to say, well, it might be an amine. Might have a nitrogen, right? Remember we looked at those NH stretches? But look, the mass spec is even. So what does that mean by the nitrogen rule? It either has no nitrogens or 2 or 4 nitrogens. Remember, an odd number of nitrogens means the molecular ion will be odd. Okay, and notice the fragments here are odd, okay, because the molecular ion's even. That's a way to figure that out there. But so this is probably not an amine here. They're often kind of small up there, but it's definitely not an alcohol. OH stretches are very large at 3,500, so it's not there. And nothing triple bond wise. That's around 22, 21. Okay, so you can already tell quite a bit about this. Now, these are problems from chapter 13, so we haven't done NMR yet. We always do the full analysis of a new molecule or a determination using a combination of all the techniques, and NMR is by far the most powerful. But we want you to learn enough about the mass spec in the IR here, okay? So let's go to the sideboard and see if we can solve this problem. This is all the data we've got here, right? We've got the mass spec saying 88 and 57, and the units, remember, are mass to charge ratio. Okay, and then the IR, we've got the frequencies here that we just summarized. So what's the structure? Can we propose something? If this is the molecular weight, 88, we can already tell roughly how many carbons and hydrogens or maybe some other heteroatoms we might have. So let me lead you through this and show you how I solve this type of problem. And hopefully this might be useful. So how many carbons might we have? Well, you could say, let's try C6, okay? Do we have 6 carbons in this molecule? Well, that's 6 times, what is it for each carbon? 12. So what are we up to here? We're up to 72. And then how do we get up to 88, though, from 72? Well, that's what? 16 more? So maybe it's 16 hydrogens. That would get up to 88, wouldn't it? Would that be okay? Would that be a legitimate formula to propose for this molecule, C6H16? Anybody see a problem with that? Can you have a molecule with only 6 carbons and 16 hydrogens? What's the problem? It's what? Right. What's the max here? The 2n+2 rule for alkanes, right? So the max would be 14, not 16. So you can rule that out. Well, what about heteroatoms? Something other than carbon or hydrogen. How about oxygen? What's the atomic mass of oxygen? You can read it up there. 16, right? Okay, so that would be a proposal. C6. Oh, You see a problem with that molecule? Try to draw a molecule that's made out of just 6 carbons and 1 oxygen, no hydrogens. Okay, so that's a problem. So how about if we lower the number of carbons? How about C5 and then something? What could we have here? 5 times 12 is what, 60? Okay, so yeah, we're quite a ways there. And what if we added the maximum amount of hydrogens? 12, we'd get up to what, 72? And then what? Oh, this would be perfect, 72. And then how do we get to 88? Using a heteroatom, oxygen, right? So how about that? C5H12O. That could work, couldn't it? Okay. But let's see here. We have a problem, and anybody see the problem here? We have the maximum amount of hydrogens. We're okay there. Okay, there are structures like this. But what's the problem here? If this is the max here, what do we need to account for here? Ah, a unit of unsaturation. We need a carbonyl, right? We wouldn't be able to have the carbonyl right here with this, okay? You can propose some structures for this, but it looks something like this, right? Count them all up there. I think that's 12 hydrogens and what? There'd be an alcohol. It'd be a 3,500 here and no carbonyl. So even though this is a good ratio of atoms, and there are a lot of known compounds for this structure here, this formula, this one is also a problem, okay? So what are we down to here? Let's try another one. How about C4, I guess? We just kind of keep going down. C4, that's what, 48 already there. And if we do oxygen here, and it's good to do the next heavier one to figure this out. So if we have 1 there, that would be 16. What are we up to, 64? And that's bad too, because then we'd have to add what, 24 more to get hydrogens to get up there? That would way exceed the 4 here, okay? So you can see by this molecular formula analysis, you're already narrowing things down quite a bit. What if we do 2 here? That would be now what, 32? And what would we'd be up here? Oh, we'd be up to 80 already. So how many hydrogens might we need to get up? Oh, we just need 8. Would that be it? C4H8O? Does that look okay? Okay, what are some structures for that? Well, how many units of unsaturation do we have here? Well, that's our carbonyl, right? We have 1 unit. The max would be 10. So we've got 2 less hydrogens. So we got a carbonyl, okay? So let's stitch a carbonyl in there. Well, we've got 2 oxygens we need to have in our structure, okay? Can you think of a functional group that has 2 oxygens and a carbonyl? Yeah, what is it? Remember the functional group? Starts with an E. What is it? Okay, ester. Okay, very good. So let's do an ester here. That's the 1 carbon and an oxygen. And then we need, what, 3 more carbons? Okay, how about this? Would that be a candidate? Yeah. Total up your hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. Yep, that would be 88 for its molecular weight. Is that consistent with all this stuff? Yeah, 88. 57, maybe here. We'll have to think about what that might be. And then CHs, yep, okay. And then the carbonyl, okay. So this one checks out. Is that the only one, though? No, there's some other options, right? What else could we do? How about just 1 carbon over here and 2 carbons over here? That would be the same thing, wouldn't it? Can we even take this to the extreme? How about just a hydrogen over here and what, 3 carbons over here? That'd be an option. Can you think of any others? All we got to do is have 1 carbonyl and then another oxygen somewhere. Do we have to have an ester? No, we could do a ketone of some kind. How about like this, a ketone, and then have what, 1, 2, 3, 4 carbons, 2 oxygen. Now it's a ketone, it's not an ester. Remember, an ester is an oxygen on the side of the carbonyl. So these are all esters except for this one. This is what, a ketone ether. Would that also check out? Yeah, maybe, okay. We'd have to go to NMR to figure out the rest of this, okay? But we could think about fragmentation. If this bond fragments right here, and we get this as a fragment ion, it will be odd. Anybody want to add up those numbers? What is it? 36 plus 16 plus 1, 2, 3, 4, 5. Ah, that's 57. Okay. So this stable acyl fragment here, this fragmentation, is actually more consistent with that. Now, I told you fragmentation, we're not going to analyze that to a great extent, but that helps you out here. For right now, the purpose of this class, we'd have to wait for NMR to figure these 4 out, and there are more, actually. Okay, but we could already narrow this down. It's got to be something like this. Okay, this ratio, this formula makes some sense. Okay. All right, let's go back to the spectra and make sure we're consistent with things there. And so, yeah, that's just what we analyzed, the 88. And from that, we got a good idea of what the molecular formula might be. The fragment here actually nails it down a little bit more, but we'd use NMR to confirm that idea of which ester we might be choosing. And then the IR really, rules out alcohols, okay? But it doesn't rule out ethers. It does, and ketones, might be a ketone, okay? And then CHs. So there's some ambiguities still there. Okay, here's one where it's a little bit more straightforward, I think, to figure out the structure from chapter 13, problem 54, I think. So it has this bromoamine here. Sorry about the condensed formula. We'll go to the board in a second. Figure this out. We say we react it with base, sodium hydride, and it forms a new compound W. And the data, the spectral data for W is shown here, both the mass spectrum and the IR. And what you see here is a mass. And we're telling you what the molecular, the M plus peak is. It's right there. It's 71. It's odd. Okay. So you already know we're not going to lose this nitrogen. It's probably going to be there, right? So 71. There's the base peak way down here at 43. And then in the IR, we see a little bit of an absorbance here or at over 3,000. And that's going to be an amine, okay? A nitrogen with 1 hydrogen on it, okay? It's smaller than an alcohol, an oxygen hydrogen hydroxyl group. It's much bigger because of the higher electronegativity, larger dipole moment when we oscillate that bond stretch there. So the amine is smaller there. So it's not an alcohol. Plus, we don't have any oxygen here in the reaction, okay? So this is coupled with a reaction. We're told what we've got here. And then, yeah, the fingerprint region's complicated, but no carbonyl here, no 1700, no triple bond. So can we figure out a structure? Let's go to the board here and figure out what we've got. So, yeah, come back over here. So what do we got for this this reaction here? We've got this bromide. And I always like the stick figures a lot better than the condensed formula. You can see them all there a little better. And then we're told, we do this reaction with sodium hydride, and then we get this compound that has 71 for its molecular ion. And it's got that little thing in the IR, about 3,200 and no carbonyl. So we can already figure it out that we've lost the bromide, right? The bromide weighs a lot, 7981 for an average a little over 80. And yeah, and you're tempted in the mass spec to say, well, we've got 2 peaks up there, but they're 1 apart from each other. Remember the halogens, it's the M+2 rule for those isotopes, right? The chlorine is 35 and 37. They're 2 mass units apart. Same with bromine, 7981. So the product here, is lower mass than the starting material. So some things are going to go on here to get to 71. So what can we say here? Well, this is a strong base, and what could we do? We can take that proton off, okay? What would we get? NH, 2 lone pairs, negative charge. And now what can we do here to get rid of that bromide and make something that's going to have a mass of 71? Well, you can add it up, right? Carbon, 1, 2, 3, 4, that's what, 48? How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9. So what are we up to here? 57. And then how do we get to 71? Well, what's nitrogen? 14, right? Atomic mass. I don't think we talked about that last time. Look at the periodic table. Atomic mass units of nitrogen, 14. Is that right? See that up there? Okay. So adding that up, yeah, look at that, 71. So we already got an idea of what can occur here, right? This could be a charged nucleophile, right? And what? This is a primary good leaving group. So it would be our product here. This is an intramolecular SN2 type reaction. And what's going to be the product? Well, it's going to have the nitrogen with a hydrogen on it and a 5-membered ring. Okay. That's called pyrrolidine. Okay. We'll learn more about heterocyclic compounds in 352. But add it up. The mass is right there for that. The base peak, let me say something about that maybe, is 70, which is M minus 1. Okay. This is the molecular mass. It's odd, the 1 nitrogen. What would be this 70? Well, if we could lose a proton off the side there, we could get this resonance stabilized cation, and that's just loss of 1 hydrogen. And these are very stable. It's called an iminium ion. We'll learn about that also at 352. Again, you don't need to analyze the fragments to any great degree, so I'm just kind of throwing that in to show you why that's such a populated peak there. But yeah, anyway. Do you see how this works, though? Combining the idea, especially with the mass spec, and then the functional groups from the stretch region of the IR. Any questions on this? Okay. Good. Let's go on to chapter 14. See what we need to know there. We've got NMR now, and NMR's the rest of the story here. So how do we know we've got what we've got? I've pointed out some ambiguities if we're just relying on mass spec and IR. But NMR here, and we can look nuclear magnetic resonance of both protons in a molecule and C13s. They're actually separate experiments. And this works because they have a nuclear spin of 1/2, which actually can resonate in a magnetic field. So we're talking about nuclear spins here. And the resonance effect here is governed by radio frequency radiation, which is actually the lowest energy form of radiation. These are very long wavelength, short frequency events, which are very low in energy. But this radio frequency, the RF pulse, will be used to take the nuclear spins out of resonance from an external magnetic field, B naught here. Okay. So it's kind of a complicated setup. I'll show you it, how the spectrometer is set up here. It's a very sensitive instrument, has a lot of very high-end electronics in it, and the strong magnetic field to do this experiment. I'll give you a little feel for that. But what we look for here is a shift range, we call. It's a kind of ppm scale, or parts per million, of the Hertz numbers relative to the megahertz of the instrument. Okay. And I'll show you how that works. The frequency applied here in the RF pulse is the frequency number nu right here, and it's in the megahertz range, which is in that radio wavelength range for the radiation. So we'll look at proton NMR mainly, and that will have a shift range of 1 to 10 ppm. And you already got a thing here. We're going to give you enough of the physics background to understand the basics of the instrument, but we're only focusing here on the practical issues of how it relates to organic structures. Okay? So don't feel too bad if you don't fully understand the physics. Okay? It's actually a complicated thing. You need quantum mechanical equations to really nail it down. But I'll show you the basics, the hand-waving argument for it. And that I think will be enough conceptually to see how it actually works. Okay, these sets of signals have to be non-equivalent, and they'll show up at different regions in the ppm range from 0 to 10. And it depends on what functional groups are part of where those hydrogens are. So if we're looking at proton NMR or hydrogen NMR, we're only looking at the hydrogen atoms within the molecule. But that's very diagnostic, right? They vary depending on what functional groups are around or how close they are to different electronegative atoms. We say they're de-shielded down here toward 10 or shielded more down here towards 0. And we'll talk about how that works, but those non-equivalent sets will use symmetry operations, the mirror plane symmetry, to determine what's equivalent and what's not. If it's not equivalent, those sets of hydrogens will show up at distinct positions within the shift range from 0 to 10, okay? This equivalency thing, we'll define that a little more carefully. We'll talk about homotopic and antiotopic and diastereotopic sets of hydrogens, okay? So those are concepts we've already talked about, right? What are enantiomers? What are diastereomers? Homotopic meaning exactly the same under all conditions and symmetry operations. So you'll see how that works. The shift is this delta value. It has ppm units, or parts per million of frequency numbers, okay? Alkyl CHs will be shielded. They'll be further down here towards 0. Okay, they're usually in the 1 to 2 range. But if they're close to electronegative groups like oxygen or halogens, they'll be shifted downfield here. They're more exposed to the external magnetic field, and they'll have a higher ppm value. If they're hybridized, if they're sp2 on a vinyl group or on an alkene, they're in the 5 to 6 range. If they're on a benzene, they're in 7 to 8 range. If they're alpha right here on a carbonyl, remember that carbon is what? Partially electropositive, partially positive. Those aldehydic hydrogens are up around 9, okay? So depending on the functional groups, these things spread out quite a bit. That's what we mean by shift. That's the most important concept in NMR. And I already mentioned a couple things. Hybridization can affect that. Now, the other thing about NMR is integration of the signals, the non-equivalent sets. When we integrate them, that's a mathematical operation, right? We take the integral of the curve of that signal. It's actually a separate mathematical calculation done by the computer, and it's proportional to the area under that signal, which is the number of hydrogens in that non-equivalent set. So we determine the type or the kind of hydrogens by the shift, and now we determine the number of hydrogens by the integration. And that's a very powerful combination of ideas, right? You can already think about that, the structures we just looked at. Some had different sets and different amounts in those sets, methyls versus methylenes versus methynes, okay? The integration tells us that number of hydrogens in that set. And then the splitting pattern, if that wasn't enough, we have another concept in NMR that's very powerful. This idea of splitting. This is the n+1 rule. N is the number of neighbors in the non-equivalent set nearby, okay? Each little spin has its own little magnetic field that can add or subtract to the magnetic field that the set we're observing sees. So the signal that we observe is actually split into a multiplet pattern. It's either a singlet if it has no neighbors, if n equals 0. You see this mathematical equation is nice, n+1. You can't get any easier than that. If you have one neighbor, 1 + 1, it shows up as a doublet. It's split by that neighbor. If it has 2 equivalent neighbors, it has a splitting pattern as a triplet, 2 + 1, right? So the concept's pretty straightforward. Quantum mechanically, it's difficult, but I'll give you a qualitative analysis of it and hopefully convince you of how splitting works. But that's a very powerful technique. The neighbors nearby split the signals we observe in a rational way that lets us know how many neighbors it has. And that's an amazing thing, okay? So we can tell the kind of hydrogens that are involved in a molecule, how many are in that set, and then how many neighbors it has. Boy, that lets us link up, and especially with simpler molecules, to really nail it down and say, oh, it must be this molecule, okay? We can confirm that with some other things, but proton NMR is by far the most powerful technique we have for molecular analysis. It gets a little more complicated if you have multiple non-equivalent sets. The n+1, m+1 rule. So this pattern can be complicated. Multiples of multiples. You can have doublets of doublets, doublets of triplets. If you keep track of the simple thing, the more complicated patterns aren't too bad, okay? And usually you only have another set Okay, it's not like you have 10 different non-equivalent sets, so don't worry. Alkene splitting, this J value, this is the magnitude of the splitting. It's in hertz. Okay, typically it's 7 or 8 hertz. If it's on a rigid system like an alkene, if they're geminal to each other or on the same carbon of an alkene and they're non-equivalent, they'll couple with a hertz of 3, okay, which is very small little doublet. If they're cis to each other, okay, if they're not on the same thing, geminal, but vicinal here, and they're cis to each other, the two hydrogens couple from 5 to 10 hertz. If they're trans to each other, it can go up to 20 hertz, very large coupling. Okay, so let's just say alkenes, cis or trans alkenes show up really well in NMR. Some more details here. Protons on alcohols or amines are highly exchangeable. They spend a lot of time in flux, being transferred from one functional group to another, so they show no splitting in the NMR typically. Okay, so we don't need to worry about splitting to alcohols or amines. Cyclohexane is conformationally flexible. Dynamic NMR, I'll say a little bit about that. Benzene can get even more complicated. You can have what's called magnetic non-equivalence or second order coupling, which is extremely complicated. And it'll just be a real forest of peaks. And we'll just discount that. But we can still measure the integration there of how many hydrogens are in that benzene pattern. So we can still say a lot about benzene, but the coupling patterns are too complicated. And then we'll do structure determinations of these simpler type of molecules. We'll look at the spectra and then, compare it with the IR and the mass spec and make determinations. These are puzzles. These are molecular puzzles. If you like solving crossword puzzles or if you like detective stories or whatever, putting together the information and then coming up with a conclusion that has to do it. Now, I'll warn you about this. Some of these can be daunting. You'll look at some of the problems at the end of chapter 14. You'll say, oh, how can I figure out this molecule? I can see a little bit here and there. No, you have to forge ahead and propose a structure. Get to the point where you can propose something and then go back and check it and see if it's internally consistent with all the data. Okay, so you have to be a little bit daring here, have a little bit of courage to propose something and then be able to check your data and see if it's fully consistent. We will look at C13 NMR. It's also a very useful technique. It has a wider shift range. The C13 atom, though, is not very abundant, 1.1% abundance. C12 is the major one, but that's spin 0, okay? The physics of the even number of protons and neutrons makes it such that the nuclear spin is silent in the NMR. It has to be an odd number of protons and neutrons, which is great for us. Protons spin 1/2, as well as C13 is spin 1/2. And there are a lot of other atoms that are NMR active too, but we'll do some two-dimensional NMR where we'll correlate protons and carbon, or we'll correlate the two hydrogen spectra. And then we'll think about or talk about 3D NMR, which is what? MRI. How many of you have had an MRI in the hospital or the clinic? By raise of hands. Anybody had MRIs? Yeah, more than half of the class. When I first started teaching, it was only 1 or 2 people in a class of 200 or so. But MRI instruments, the same basics of it. They don't like to call them NMR instruments in the hospitals because people ask, well, what's the N stand for? Oh, nuclear. I'm not getting in a nuclear device. Sorry. Okay. It's easier to tell people, oh, I'm getting in an MRI donut. It's a nice donut-shaped thing. Well, that's the big magnet, okay? We have to have the permanent magnet. And then for MRI, we actually look at the spin densities of the proton and the phosphorus nuclei, which are, of course, in nucleic acid materials in the nuclei of things. This image is soft tissue. It's a great complement to X-rays, which images hard tissue, bones, and things. But with NMR, we see a lot of contrast and much more detail. This is becoming the standard medical imaging device. So NMR itself becomes more important to people going into the health sciences. Here's what the device looks like. We've got a few of these in our department. We have 2 500 megahertz instruments, a 300 and a 200 megahertz machine. When I was an undergraduate, the standard machine was a 60 megahertz machine, an iron core stationary field instrument. These are supercon magnets now, superconducting electric coils here. which perpendicular to that is a strong magnetic field. Now, a 60 megahertz machine goes up to 14 Tesla or 14 megagauss. These are very powerful magnets. If you go in a room and get close to a machine like that and hold your keys like that, your keys all of a sudden will go horizontal. Okay, and why is that? These are very strong magnetic fields that can be created. It'll also wipe out all your credit card information on your magnetic tape on your credit card, and it'll bother people with pacemakers. So it will, because of the strong fields here. Supercon magnet, the sample goes in the top. It's in a little 5 millimeter tube that's about 8 inches long here. This is the permanent magnetic field. I'll show you that. And inside are RF coils to generate the radio frequencies, which are actually pulsed into the sample then. And then there's a set of detector coils. Okay, and it's spectroscopy, right? We apply the radiation. We measure how much is absorbed. Okay. Remember, the basics of analytical chemistry still hold here. The problem is we're looking at parts per millions of wave numbers and frequency numbers, which are very small, okay, relative to the magnetic field frequency. So we need very sensitive electronics. The electronic console here is part of the cost of this instrument, which is very expensive, $1 million or so for a simple high field instrument here. And then, of course, a computer console where we actually see things come out. So let's look at an actual spectrum. So here you have chloroform. There's only one hydrogen here, okay? And it resonates down here at 7.2 ppm. And I'm also showing the Hertz scale down here. You notice ppm, here we're talking about parts per million. I'll show you the equation for that, or delta. Sometimes we just say delta. But what this means is parts per million of the Hertz numbers, the frequency numbers, out of the frequency of the instrument. We have an internal reference standard. This is tetramethylsilane, which is highly shielded, and it can be normalized or referenced to 0 ppm. And then everything else in most organic compounds is downfield or more deshielded relative to tetramethylsilane, okay? And you see here, chloroform is actually quite deshielded. It's down here at 7. It's not a typical alkane because of the 3 electronegative chlorides. We'll have to talk about that. What affects the shift value here? Here's another sample here. This is what, tert-butyl methyl ether. Sorry about in the condensed form here. And now we're analyzing what? We have 3 different signals showing up. Well, that's the TMF reference at 0. And then we have a big tert-butyl, okay? And all 9 of those hydrogens are equivalent, and they have no neighbors. So it shows up as a singlet. But its shift is down here at 1.2. Okay, because it's an alkyl thing, and it's 2 carbons away from the oxygen. We say it's shielded from that oxygen. The oxygen is, of course, electronegative, so it deshields the methyl group that's directly on that oxygen. So this methyl here is different than these 3 methyls, right? You see it down here at 3.2 or so ppm, and we could integrate this, and what would be the integral counting the area under this peak here? It would be 9 to 3 or 3 to 1, okay? So it gives us a lot of information about that. But let's look at this and let's talk about the basics of NMR. And we're going to go to the board here now, Colin. So how do we figure this out, and what are we going to talk about? Well, I always like to review the bottom line here. NMR, it's the 3 things. And as you get into NMR and start working the problems and reading about it, it's easy to get lost from these key ideas. The key idea is the shifting the frequency. That's what we mean there. The units will be delta or ppm. And this tells you the kind of hydrogens. Okay? And they're sets. And these sets, we say, are non-equivalent. Okay? And that's kind of a key thing to keep in mind. Okay? So each non-equivalent set will show up at a different frequency or have a different shift, okay? And that's by far the top thing to keep in mind. The next thing to keep in mind is integration. And what do we mean by integration? We mean the number, okay, of H's in each set, okay? You already got a feel for that, for the tert-butyl methyl ether, integrating 9 to 3, or what, 3 to 1, if you divide by 3 both there. But that tells us how many numbers are in there, right? And then the third thing to keep in mind is splitting. And this splitting thing are multiplicity patterns. And the multiplicity pattern depends on how many neighbors it has. N stands for the neighbors adjacent to what we're observing. So if you got no neighbors, if you're kind of lonely there, it'll show up as what? A singlet, okay? If you got one neighbor, it'll show up as a doublet, okay? So that's what these little designations mean. And then if you've got two neighbors, it'll be a triplet, quartet. Those are the common ones, doublet, triplet, quartet, when we got molecules that have multiple neighbors. And then we have pentet, we have hextet, and on up, but that's a lot more rare, okay? Usually then we're having a more complex pattern that has different things here. But this multiplicity then tells us what? The number of neighbors, okay? And that's a very powerful technique because then we can link up different fragments that we think about, okay? So it's the combination of these three things that let us know how this works. Okay, questions on it? Always keep this in mind, the basics of NMR and what we're talking about. All right, let's get into a little bit of the physics, not much. I'm not a physicist. I know some physicists, though. We have an NMR expert in our department, Dr. Scott Burt, teaches our NMR classes and manages our NMR instruments. He got his degree in physical chemistry at Berkeley. It's very good. If you want to know more about the details of NMR, feel free to talk to him or sign up for his class. Nuclei have spin. Okay. What do we mean by this? Well, the nucleus is the heavy part of the atom, right? And this thing can spin. And as it precesses or spins, it creates its own little magnetic moment, mu bar, okay? And this is a particle, right? It's a physical object. We're not talking about electron excitation or anything like that. We're talking about the spinning of the heavy nuclei within a molecule. Now, usually these are randomly distributed, but if you put this in the presence of a large external magnetic field, the spins will line up against and with the magnetic field. It's actually a small proportion that will do that. We say that the nuclei then have spin of plus 1/2 or minus 1/2. And those are quantum mechanical numbers. Don't worry about that. You can actually measure the angular momentum of them. But if it's lined up with the field, it's spin plus 1/2. If it's against the field, it's spin minus 1/2. Now, think of it this way. So here's the nuclei, okay? And I have one object here, so it's a single fishhook arrow. And the arrow implies, you know, a magnitude of the spin. Let's say it's lined up with the magnetic field, okay? Now we apply an RF pulse, okay? This is a separate part of the spectrometer. It's a set of coils that are perpendicular to the sample that's in the tube, okay? So at equilibrium, we say the spins are aligned with or against the field, okay? We haven't applied the pulse yet. But when we apply the pulse, it depends on this frequency of the pulse, okay, which is specific to the spectrometer and specific to the different types of nuclei and how they're either de-shielded or shielded. They can have little variations. That's the ppm variation there. This pulse here is the RF pulse that then sympathetic to bringing that spin out of resonance with the external magnetic field. So yeah, I'm using the term resonance, which we've used for movement of electrons before, but this is a different type of resonance. We're talking about being lined up with the magnetic field or against it. And when we apply the RF pulse, we can tip that spin out. Okay. So the spin is now perpendicular. Okay, we've wiped out its ability to line up with the external magnetic field. So that's B naught, which is very, very large, okay, which is aligning a different number of spin. So we're tipped out of resonance here, and then we watch the thing come back. And that's the detector. Okay, so there's two sets of coils, the RF coils that apply the radio frequency, and then the detector, which actually sees it come back into resonance. Okay. Now let's talk about this this frequency, this pulse right here that does this. This is megahertz, okay, which is in the radio frequency range. If we have a magnet of 14.1 megagauss or Tesla, maybe you've heard of Nikola Tesla, the famous, he was an electrical engineer. I think he was from Croatia originally, but he set up the alternating current grid. Remember the electrical grid competition between Tesla and Edison? Edison had the direct current system. Tesla had the alternating current thing. And he was into electromagnetic dynamics, right? Which has to do with magnets or Gauss. And this is a huge number, mega Gauss, and Tesla named in his honor. This corresponds to a 600 megahertz machine. Okay? And this can vary depending on what type of a magnet you have. This hertz value is also proportional to the magnetic field, of course, 2 pi. This is the basic equation for NMR. This is the hertz of the radio frequency that needs to be applied, and it varies depending on the strength of the magnet. And this gamma value here is called the gyromagnetic ratio. It's how sensitive this particular nuclei is to this. So if it has spin 0, if it's an even number of neutrons and protons, it'll actually be spin 0, and there's no frequency. It's silent in the NMR. It's got to be plus. But these can vary depending on the nuclei. Some nuclei are very sensitive to NMR, some are less sensitive. So this depends on this gyromagnetic ratio. But you see the frequency is directly proportional to the strength of the magnet here. So if you have, for example, a 4.1 megagauss machine, that would be a tenth of that value, and that turns out to be a 60 megahertz device. And that's what I started out on as an undergraduate. By grad school time, we had 300 and 500 megahertz machines, so they've increased greatly here. But then the frequencies are a little different, right? And we'll have to look back at the spectra and see what this means. Let's do the equation now to figure out the delta value. The basics of the instrument, you have the idea of what's going on electronically, at least with it. I saw a couple hands, yeah.
So the instrument is measuring when it goes from vertical to horizontal back to vertical.
Yep. So the question was, what's the instrument actually measuring? It's the spins coming back into resonance with the external magnetic field. So you see at what point the molecule's absorbing the radiation. Okay, so that's what the peak goes up. It's absorbing radiation right there. It's being tipped out of resonance with the field, and then you see it come back in, and that's the back part of the peak as it decays back in to resonance. Yeah, so it's a lot of very sensitive electronics, but that's exactly what's happening. The equations to cover it are pretty straightforward. So the ppm value or the delta value, the shift, is always normalized to TMS, which is tetramethylsilane, which has a shift or a delta value of 0. Okay, it's a highly shielded molecule, so we can always tell that. So the shift here, or the delta, is equal to the position of the sample or the set. Okay, because you can have multiple sets in a molecule, right? Minus the position of TMS divided by the hertz of the spectrometer, and that's the magnet, okay? So let's see for a sample here, chloroform, that we'll go back to and show you that. It's 437 hertz minus 0 hertz. If you normalize it to TMS, that's always a good thing. Then it's just directly what the hertz of that are relative to the magnet, which is 60 times 10 to the 6th hertz for the magnet. So that's 600 megahertz. Okay, and you can see the part per million amount right out of that, right? So what do we get here? If we do the math, we get 7.28 ppm. Okay. And why do we call it ppm? Parts per million. The hertz that's shifted out of the million of hertz for the magnet there. And it does depend on the strength of the instrument. So you can see here, if we're at 60 megahertz, 1 ppm will be equal to 60 hertz. Okay, that range of like going from 0 to 1 or 2 or 1 to 2, whatever, each ppm range there will be 60 hertz. But if we're at 600 megahertz, we could do the same thing. Then this would resonate at 4,000, right? This would be times 10 there. And each ppm there, 1 ppm, is equal to 600 hertz, which lets us have higher resolution of the shift patterns and the splitting patterns, which are very important. We get better baseline resolution. So it's better to have the highest possible magnet strength possible to get the best resolution. You don't necessarily need that if you got a smaller molecule. They make 800, they make 1 megahertz instruments now, which are very expensive and are only needed for big biological molecules like proteins or whatever. But that's the basics of it. And like I said, it's got to be spin 1/2, and the proton is spin 1/2, okay? And also C13 is spin 1/2. C12 is spin 0. It's silent. So when we get to C13 NMR, we'll only be looking at the very unabundant isotope there. All right, let's look at the, running out of time. Maybe it's better just to stop right here. But next time I'll give you a little history of NMR. We'll talk about Bloch and Purcell, the people who won the Nobel Prize for developing NMR, and how they handled their grad students and how the grad students built the first instrument and what sample they used and what actually came out of the data. So stay tuned for that. We'll give you a little history discussion next time. And we'll get into solving the problems of it. So these next 2 classes are very important for NMR, next Monday and Tuesday. So plan ahead there. Start working some of the problems if you want in 14. Look for those 3 key things. Let's just review that real quick. What are we looking for? The shift, or the delta value for the non-equivalent set. And number 2, we're looking at the integration, how many are in that set. And number 3, what's that? The splitting, how many neighbors they have. Always keep those 3 things in mind. That'll help guide you through the complexities, I think, of